Thanks, great. Thank you. So let me just quickly set up everything that I see it correctly. Okay, I will get the questions here and let me put the, all right. Yes, okay, cool. Yes, hello everyone. I'm very happy to be here virtually, basically, to talk to you about blockchain. And it's supposed to be kind of a more or less high-level overview, but also with a lot of technical stuff. And my goal is that after the talk, you have a better understanding of blockchain as a technology and how it might apply to you in the future and where it might make sense to use and where not. And basically what is behind all this buzzwordy stuff and hype behind blockchain. The hype is a little bit gone nowadays more, but still historically it's kind of a hype. We also will see some code examples about how to implement a blockchain in Java, like just for fun, why not? Yeah, that's it. So first about me, my name is Kevin Wittek. I'm a doctoral researcher at the Institute for Internet Security in Germany at the Westphalian University of Applied Sciences, where I'm leading the blockchain research lab. I used to work in the industry as a software engineer, but I then went back to academia and to the university to do my PhD. And yeah, accordingly, I do my PhD in the field of blockchain and distributed systems engineering. I've amassed a lot of side activities by now. So I'm also working on kind of a blockchain-based product or startup thing. It's called Lithium. And a lot of people know me in the Java and open source community mostly through my test containers activities, because I'm one of the maintainers of the test containers Java library, which is a open source library for integration testing using Docker containers. But we will not talk about test containers today. And I'm one of the Oracle Groundbreaker ambassadors, and that's also one of the reasons maybe why I'm here today in this, giving you this talk as part of this virtual tour. And there are a couple of blockchain communities where I'm involved: Bloxburg, Sovereign, ICC, whatever. You probably never heard of them, but some of them do pretty cool stuff in the domain of blockchain. So the title of the talk is Blockchain Through the Looking Glass. Maybe not many people are aware of what I mean or what was my intention behind the Through the Looking Glass, but this is actually the title of a novel by Lewis Carroll, who wrote Alice in Wonderland, and it's kind of the sequel to Alice in Wonderland. And in this sequel, she finds out that after she returns from the Wonderland, that when she looks into her mirror, she finds out there is a world behind the mirror where a lot of things work different than in the real world. And yeah, I thought it was a cute spin about blockchain as this like hype and mysterious and potentially magic technology or whatever. And we wanted today look behind the mirror, behind the looking glass, to find out what actually is blockchain, because it has a lot of basic computer science building blocks that are really nice to know. And it's, in my opinion, a good thing to go away from this more hypey and sometimes a little bit bullshitty stuff we all learned about blockchain in the past, maybe. If at any point in the talk you have any questions, like, feel free to just put in the questions in this Q&A section, and I will try to answer them as soon as possible. I would be very happy if we can get some interactivity going here, although we are just here in this virtual meeting now. And I like to give you a little bit of a historic context, because it is possible, if someone wants, to spin a narrative that actually starts with the very early computing system and goes to blockchain and blockchain networks nowadays. And it is basically the story of the first time-sharing operating system, and nowadays to this world computer and network of networks which one can imagine blockchain might enable. We see here Dennis Ritchie and Ken Thompson in the 70s, basically while they are inventing or programming Unix. And it might make sense to classify at least the public blockchain networks as a class of utility computing. So utility computing is kind of a widespread thing, but maybe not many people think about what utility computing actually means. And in a certain way, it started in the 60s. when they invented the time-sharing operating systems. Multics was the first one, and then Unix came as a development afterwards. And what was really so interesting for me to find out was that back then the developers working on this time-sharing operating systems, they were thinking about computing resources as a public utility resource that everyone would use depending on their needs. That was the idea behind the time-sharing operating systems. So modeled after things like telephone networks or the electrical power grid, etc. And they really had the vision back then that all those different universities that would have some mainframe big computer systems, that they would connect in a network, and this would be a shared resource that will be used by others, by developers, by users, and basically paying and using the resource based on your usage. So already a lot of these network things back then. And then later we had with the ARPANET, that later became the internet. And then, of course, the World Wide Web later, we have the development of this real network and the internet as a network, which is in a certain way a utility computing resource that is shared and used by all of us. And cloud computing was also a certain way to make this utility computing based on resource usages more accessible to a lot of people and make it a widespread thing to do. So AWS was, of course, the first cloud provider. Nowadays, we have many others, also Oracle Cloud. We have IBM, Google, Microsoft, all the big players. And while this provides computing as a utility resources, at the same time, we see a certain factor of centralization actually happening. So more things are closing up in those big, like very big cloud silos. So not saying it's a bad thing, but it's a certain kind of centralization as compared to the actual decentralization goals of networks. And in a certain way, Bitcoin changes this rules of the game a little bit. So Bitcoin is probably one of the most well-known blockchain networks, public blockchain networks. And you can think about the Bitcoin network as a decentralized state machine that will self-synchronize on a certain state. But it mostly just holds a state and a worldview, a synchronized worldview on the state. And then in 2015, we have Ethereum coming up. So Ethereum is another blockchain technology, basically, and also another blockchain network. And Ethereum now also provides us basically a Turing-complete virtual machine. So we not only have a decentralized state machine now, we also have a programmable decentralized state machine. One can say is kind of a world computer, a very slow one, but it is one, and that's kind of cool. And now following this stuff, we now have some movements for moving to networks of networks, like blockchain networks becoming more interoperable with each other. And the interesting thing about blockchains is that they always talk about the concept of trust. And the first like publication about Bitcoin, which was the original paper by Satoshi Nakamoto, which is a pseudonym, so we don't know who actually invented Bitcoin and wrote this paper. But it says in this paper and in this abstract that we have proposed a system for electronic transaction without relying on trust. This is a narrative you always find around blockchains. They will tell you, okay, thanks to blockchain, we don't require trust into classical trust infrastructures anymore. So, but I would challenge this actually. I would say trust is still necessary. It's just a new form of trust. So classical trust infrastructures, architectures, we know as a human society, and that also is reflected in the systems we design and develop, are things like peer-to-peer trust. I'm trusting another person. We have something Leviathan trust. We are trusting that society will uphold certain laws, and trust in an intermediary that we execute every time we do a banking transaction. We are trusting our bank to execute the transactions as we want, as we specified. And now what changes because of blockchain technologies is a new trust architecture, which is now defined as distributed trust. So you're now trusting the correctness of a distributed system, like of a set of nodes operating, and their protocol and the code that implements their guarantees, basically. So this is a new thing. You still need trust, but it's a new form of trust. And already in the 80s, we have a very cool quote by Ken Thompson from the lecture he gave when he got the Turing Award, Reflections on Trusting Trust. To what extent should one trust a statement that a program is free of Trojan horses? Perhaps it is more important to trust the people who wrote the software. And I completely agree with him here. And this is something I would like to bring to the table, to the topic of blockchain and trust in blockchain as well. So people can tell you all the time, all they want, okay, when we use blockchain, we don't need trust anymore. We can trust the blockchain. This is basically a lie, because we, in the end, then trust the people that wrote the code that runs the blockchain. And this is very important. And even if the blockchain is open source, we all know open source alone, like although Linus Torvalds said, given enough eyeballs, all bugs are shallow. Even we have the saying, we see those very critical bugs, security bugs coming up in this very big open source libraries like OpenSSL and so on all the time. So just because something is open source doesn't mean by itself that it will be super high quality, that it will be audited, and that it's trustable. So this is an effort we as an industry still have to invest into a technology. Okay, then let's jump a little bit around to the history of Bitcoin and how this whole Bitcoin blockchain craze started. And this is, of course, a story of cryptocurrencies. 2008, Bitcoin was published as a concept in the paper, Bitcoin, a peer-to-peer electronic cash system. And then in January 2009, it basically became live by mining the first Bitcoin block, the so-called Genesis block. So the first block of a blockchain is a Genesis block. And we see here the load in the Bitcoin network, in the public Bitcoin network, so number of transactions per month. And we saw a constant increase. And nowadays we are more or less at a saturated level of maybe 10 million transactions per month, which seems a lot compared to the low values we had in the beginning, but which is tiny compared to like credit card transactions, Visa transactions or whatever. So it is still a very niche system. And also we have a certain saturation in the speed now, in the speed at which these transactions can be executed in the network. At the same time, and this is probably what Bitcoin is very famous for, and what also gave a little bit of the better reputation to blockchain in general. Like people say, oh, Bitcoin, blockchain, it's the same thing, but it's two different things. Bitcoin is one example of a blockchain system. And this problem is the volatility of Bitcoin as a cryptocurrency. So people assume Bitcoins have a certain value in the real world currencies, in the so-called fiat currencies, but this value is highly fluctuating and is basically comparable to other financial markets, like how you call it on English, like the Wall Street stuff and so on. Yeah, so very volatile, even more volatile maybe, and unexpected, and therefore this got the whole story of being kind of a bubble, because those volatility kind of leading to very high fluctuations. But in a certain part, this just shows something that Bitcoin was not envisioned for, because we see here now Bitcoin as a speculation object, and that was not the idea of Bitcoin. Bitcoin was really intended to be this more or less intermediary-less transaction system, and not for holding and investing into Bitcoin. That is not the idea, the original idea. Yes, and of course, we nowadays have many other cryptocurrencies. Every day a new one can come up, and you can easily spin up your own Ethereum network and in a couple of hours invent your own cryptocurrency, no problem, very easy. It's a list of top 10. But the most important one, in my opinion, are Bitcoin and Ethereum, if you are thinking about blockchain in the context of cryptocurrencies. Now, what is a little bit more interesting, in my opinion, is looking into the technical properties of blockchain system. And we want to look into them by using Bitcoin as an example, because Bitcoin is a good example, since Bitcoin is quite simple as compared to other blockchain systems. And in case of Bitcoin, it's a decentralized peer-to-peer network, and most blockchain systems are peer-to-peer networks. So we don't have central servers that have cluster or whatever. No, we have like these different nodes in the Bitcoin, in the blockchain network are peer-to-peer, communicating using certain peer-to-peer protocols. And those protocols are sometimes very similar to these old file sharing protocols, for example. Then there's something called a distributed ledger, a public distributed ledger. This is the core idea of all those blockchain systems, and it's such a core thing that we now have a new word for it. We call it distributed ledger technology. And it's supposed to be a little bit more abstract than blockchain as a word. Distributed ledger means just like is a append-only ledger that is, yes, distributed public, everyone can see it. And blockchain is one way to implement such a data structure. There are other ways, like more network-oriented tangles and so on, doesn't matter. And then what Bitcoin is very famous about is the proof of work-based consensus mechanism. Also something Bitcoin gets a lot of bad reputation for, because people say because it's proof of work, it uses so much energy, it is very wasteful. Yeah, there's some truth to this, but we will look a little bit in the technical properties. So it's based on Hashcash proof of work algorithm. We will look into this in a bit. And it leads to the Bitcoin network being Byzantine fault tolerance to basically less than 50% malicious actors in the system, which is very good. This is a very good Byzantine fault tolerance degree. So most normal Byzantine fault tolerance algorithms will only provide against 1/3 of malicious actors. By the way, Byzantine fault tolerance means in distributed systems theory how many of the actors in your system can send wrong messages. Not necessarily malicious. It could also just mean like bugs or errors or whatever. And how resistant the whole system, distributed system, is against those kind of failures happening. Byzantine fault tolerance. Yes, and but still, it is attackable. So if you are having 51% controlling 51% of the network, which we have seen happen in the past, you can attack the network and therefore introduce malicious transactions, more or less. And there's one interesting thing that by participating in this proof of work, you are getting a certain amount of Bitcoins. This is this famous mining idea. And the whole idea, and this is a very clever idea at its core, is that it's more profitable for you to be an honest actor in the system and participate in this proof of work instead of attacking it. So instead of using your computing power to attack the network, you earn more by just being an honest actor. Very clever solution to this Byzantine fault tolerance problem. Blockchain as a data structure, however, one might argue is even older than Bitcoin. And I like to say it's maybe as old as the 80s or the 70s potentially. So in the 80s, we have the dissertation by David Shawn, computer system established, maintained, and trusted by mutually suspicious group. Very active person in the whole blockchain and cryptography sphere. And here he already talks about concepts of chaining checksums together. Yes, and one could say this is the core idea of a blockchain, because how does the blockchain data structure look in a simplified view? The idea is you take a block that contains a number of items, in case of Bitcoin transactions, and this is the input for a hash function plus the hash of the previous block. This is then the hash. Okay, and then if you get a new block, you take this previous hash, it goes in there, you hash the new block, and then you have your new hash. And by adding all those blocks, each subsequent block is securing the previous ones. Because if you would want to manipulate a previous entry, you need to recalculate all those hashes. Now, recalculating those hashes in itself is not necessarily super expensive if you are controlling the system alone. But in case of Bitcoin and most public blockchain networks, the whole distributed system, the whole network is controlling the blockchain. Therefore, it becomes very, very hard because you have to convince the majority of the network that your now recalculated, manipulated blockchain is the correct one. And that's only possible if you control, in case of Bitcoin, more than 50% of the network. Now, in case of blockchain, in case of Bitcoin, the actual data structure looks a little bit different. So we also have this nonce thingy, and this nonce thingy is the result of the proof of work. Is a solution of the proof of work. We will look what it means in practice in a bit. Before we look into how we can implement such a proof of work in Java, I like to give a little bit of history to proof of work as well, because also here we have a rich history that doesn't start with Bitcoin. In the 90s, 92 actually, we have probably the first concept of using something like proof of work in the paper Pricing Via Processing on Combating Junk Mail by Dwork and Nauer. And the idea is with regards to spam mail, junk mail, which was already a problem in the 90s. It was envisioning a system for paying resource usage costs for something that is basically a free resource. So sending emails is more or less free. That's why we have the problem with spam, because no one is paying for sending the spam. So it's so easy to send so much spam. And now they envisioned that users who want to say to send an email have to solve a pricing function, so pay with computing power they invest, that is cheap enough that a normal user, for him it's basically still free, but malicious actors, for them it becomes too expensive now to send spam mail. Yeah. And then in 99 we had the first paper that first uses proof of work even as a word. Proof of work and bread pudding protocols by Jacobson and Jules. It adds on top of this concept by thinking, okay, maybe this pricing function could be something useful we can reuse for something. And what they want to reuse it for is finding hash collisions. And these hash collisions are coins, are micromint coins. So here we already in the 90s see this concept of generating coins through investing calculation power, CPU resources, and actually by defining points as an identified hash collision. And now the cool thing is that's exactly how Bitcoin also works. And Bitcoin takes its proof of work implementation from 97. Adam Beck, who he says he wasn't aware of the other works at this time, and I'm inclined to believe him, but he invented or reinvented the same concept of solving this spam mail problem by the hash cache, using the hash cache algorithm. So, system for throttling abuse of unmetered internet resources. And clients need to find a partial hash collision, and then they add this partial hash collision to the header of the email, and the other email servers, the relay or whatever, it will only accept the emails if a valid hash collision has been found. And for this, basically certain metadata of the email, for example, is concatenated, and then a hash of them is created. And now you have to find a hash that starts with a certain amount of leading zeros. This is the partial hash collision. Finding a hash that, for example, starts with 3 leading zeros or 5, whatever. And now you have a counter, you just increment one by one to finally find on a brute force way this hash collision. And that is proof of work. And that is a proof of work how it works exactly in Bitcoin. And let's check out how it looks in Java code if we would implement this, because it's actually fairly simple, and I like how simple it is. So I have a Java class here, and now I specify here just some difficulty. And this difficulty tells how many leading zeros I want to find. So this is a partial hash collision I want to find. And yeah, this is now some stuff I'm doing here. Let's check at the actual implementation. So we have a block, and we define a block. Now here's a little bit simpler than in Bitcoin. We just say a block has some data. It has a previous hash, and it has a nonce that initially is 0. Now, if we want to mine a block, all we want to do is we want to calculate the hash of the block. This is the hash calculation function. We say the hash is simply the SHA-256 of the concatenation of the previous hash, the data and the nonce. And we will now go on calculating a hash until we find the partial hash collision. So a hash that starts with the difficulty, which was 4 leading zeros. And we just increment this nonce by 1. And by the way of how cryptographic hash functions such as SHA works, there it doesn't matter if we just increment by 1 or by 2 or whatever, like the hash values are evenly distributed more or less, so we can just brute force try one after one. And then when we found this, we mined this block successfully. And yes, we can run this here. So we just mine some data foo into a block, then we create a new block, add the hash of the previous block, mine it again. Okay, and we see, for example, the first, it took 700 milliseconds. Mining the second block took 300 milliseconds roughly. And just by looking at the nonce, we see how many values the computer had to try out. Quite a lot, actually, like nearly 100,000 values. So it were 100,000 hash calculations we had to do also. Yeah, that's something to keep in mind. And if we just increase the difficulty, we will see the whole proof of work becomes much more CPU intensive. So yeah, now already nearly 2 seconds. And we see here it's 2 million calculations. So that's quite a lot. That's quite expensive. And I'm not sure how long the difficulty right now in the public Bitcoin network, but yeah, that's mining. And now what people use, they use, of course, specialized computers that are very good in doing this SHA calculations of the hashes and so on. But yeah, that's the proof of work of Bitcoin in a nutshell. Nothing more, really. And still, it's a clever thing for solving this research, like for solving this problem of paying for free resources, basically. Just we have the problem now with regards to Bitcoin, that Bitcoin became a speculation object, and therefore it became so economically useful for people to invest huge amounts of money into the mining, and therefore it's now an environmental problem to a certain degree. But that was never the intention of Bitcoin as a system, how it was designed. So with blockchains, there are basically two kind of camps of people. One is the very extreme camp who say, okay, blockchains are only then really blockchain systems and open blockchains, open networks, if they apply to these 5 pillars. So they have to be open, borderless with regards to nation borders, neutral, completely censorship resistance, completely public. But there is also another class of people that says, okay, different blockchain systems can reside on a certain spectrum or can be implemented along different dimensions. And then we find those definitions of blockchain networks that can fall into those 4 different quadrants. So we have those famous public open blockchain networks, such as the Ethereum one, such as the Bitcoin one. But then we can also envision very private blockchain systems that are operated by a certain set of organizations, businesses, for example. And then they are called, for example, those private closed blockchains. If any of you used ever Hyperledger Fabric, Hyperledger Fabric is normally a private and closed system. Private means only authorized users are allowed to read the data, and closed, open versus closed, means who is allowed to participate in the mining or in the validation of blocks. And there are all kinds of combinations. So another one that is very famous nowadays is private open. No, actually public closed. That is the correct one. So sometimes this taxonomy is a bit confusing, because it's also, people like to call it public permissioned and public permissionless. public permissioned would mean the data is public for everyone to read, but you have a certain set of validators that are only allowed to mine blocks. And then you can use other consensus algorithms that are much, much cheaper as proof of work, for example, proof of authority. That is used in a lot of currently rising blockchain infrastructures and blockchain as infrastructure as a service projects. Another thing which nowadays you have to talk about when you talk about blockchain is smart contracts and the concept of smart contracts and what they might allow for. It is basically the way to bring behavior into blockchain. Blockchain itself is just data and state, and by adding smart contracts, we can get behavior to act upon the state. Very cool. People in the blockchain and smart contract world like to cite Lawrence Lessig, who once mentioned code as law. But they like to cite him wrongly. Therefore, I like to take the opportunity to correct his quote whenever I give such a presentation about blockchain. And so smart contract already has the notion of a contract, but it really is not a contract in the human sense, in the human society concept of a contract. That is quite important for me to highlight here. But then always people said like, oh, Lessig said, we will write code, we will encode our laws, encode our human laws and so on. And he never said this. What he said was that we have to be, and this is quite old actually, this post, this article from him from 2000. He said, we have to be very careful with the speed that the cyberspace is developing. So like the internet companies, etc. We have to be very careful because if they take up the speed, we will not be able to adopt our laws accordingly. And then at one point, those technologies, those companies will have so much power that they will encode the laws by which our society will operate. This is a big danger. And so I'm German and I'm from Europe. And in Europe, we are a bit like carefully with those data privacy topics. We have things like the GDPR and so on. But still, this is a reality, basically. So the European Union can bring out a law such as the GDPR, and companies such as Google and Microsoft still can say, okay, we don't care. We pay our fines, but we don't care about the user data. We want to have it all. So I think this danger became a reality in a certain degree. And it's a problem of centralization to a certain degree and power. And there are people who say that blockchain can help in equalizing technology more because of the decentralization. I also like to believe in this, but we will have to see. It's a far future vision, maybe. Oopsie, yes, this is Lawrence Lessig. So smart contracts as a concept itself also very old, from the 90s, from a paper by Nick Szabo. And he has this very useful example of the easiest smart contract possible. Is a smart contract. It's a piece of code that executes a business transaction. And he says the business transaction that is performed when you pay something in a vending machine is the very, very primitive ancestor of smart contracts. And I like this very much. You put in money, there's a certain code that executes if you put enough money to get a certain product, and then it gives you the product, and therefore you execute this business transaction. Very cool. But he already envisioned more complex scenarios where you would have some sort of cryptographic keys that is attached to a certain amount of payment, and it could unlock other cyber physical objects such as cars and say, okay, you paid your monthly leasing rate or whatever, now you can unlock the car. So that was his idea of smart contracts. And then, as far as I know, the first technology that made this a widespread reality was Ethereum, as envisioned by Vitalik Buterin in 2013. And then we have Gavin Wood in 2014 actually designing the implementation by defining the specification of the Ethereum virtual machine. And Gavin Wood is a super cool guy who made his PhD about music visualization, by the way. So really cool. And one can say like Ethereum network is a Turing complete world computer, and it provides something called rich statefulness, which is cool. So it's on one hand is a Turing complete and it's this decentralized state. And at the same time, this rich statefulness means we see the history of all states it had over the course of time. So it's like built-in auditing, basically. Nice. And now if we develop applications that interact with smart contracts, they are called DApps, decentralized applications. And there are all kind of different networks that use Ethereum as a technology. So different Ethereum networks. We have Ethereum mainnet as a network, but we also have Ethereum as a technology. And there are different networks that use Ethereum as a technology to spin up networks. And one famous one is Bloxburg. It's one where I'm participating in. But you could also imagine private networks being opened in some clouds, and the clouds already supported. Oracle Cloud supports it, Azure has it built in, etc. And this is a source code example how a smart contract looks. It looks surprisingly similar to a class in Java, I would say. And it's in a nutshell very, very similar in a lot of concepts. So instead of a class, you have here contract. Okay, this is a storage contract, and can also have something like a constructor. We don't see it here, but it can have. So it has a state variable. This is field, number field, and it can have functions to act upon the state. And when you deploy a smart contract, you get an instance of the smart contract running in the blockchain, a certain address. This is the same as instantiating a class, and then you have an object that runs in a certain address in your memory. Just with the smart contract, it runs in a certain address in this decentralized network. But I think from an idea standpoint, it's very, very similar to something like object-oriented programming, just in this distributed network. Cool, from an idea, cool, and not complicated. Is basic computer stuff, basic programming. Yeah. Okay, this I will skip. This is a more complex topic of consensus protocols. But what I want to show in the end is how to interact now with a smart contract from Java. And for this, we use Web3j as a library. Works very well. So let's check this out. So first of all, I have here this smart contract in Solidity. Solidity is a language in which you can write smart contracts that will then be compiled into Ethereum bytecode. I have here a Maven POM. I have Web3j as a dependency, and I also have a plugin, Web3j Maven plugin. Now, when I, sorry, Maven. I want to open the Maven window. What I do like this? No, not like this. Yes, this I want to do. All right. So I now get this additional plugin method from Web3j, generate sources, which I will just run here quickly. Let's hope it still works. I haven't tried it today. So what this does, it takes this Solidity smart contract and it compiles it and it generates Java proxy classes for it. Pretty cool. Those Java proxy classes you can then find where? Java, yes, here, storage. This class contains the bytecode of the smart contract. You can then use this to deploy it somewhere. And it also contains generated functions for interacting with those smart contract functions, store and retrieve. And they are all remote function calls, so calls over the network. And now let's quickly look how we can interact with the smart contract. Okay. Wait, this is not the one. Sorry. Oh, I just have it in as a Groovy example, but okay. So it's not Java, it's Groovy. It's even cooler. Then you see some Groovy here as well. So now what I'm using also, I'm using this local Ethereum environment. It's called Ganache. You can use it to spin up a local Ethereum blockchain. And now I have a certain amount of addresses, accounts here already that have some Ether. You need Ether to pay resource usage on Ethereum. So I'm taking here the private key. Just disclaimer, this private key is hereby burned. It is not a valid secret anymore for anyone to use in the future. It's just some dummy work development stuff here. So I'm adding this here. Now what I will do, I will create a Web3 client that connects to my locally running Ganache-based Ethereum network. And then I can use the static functions on this smart contract proxy class to deploy it to the network. So you always have to then execute send to do the actual HTTP call. And now I can interact with the functions of the smart contract, which, as you see from the send, also always goes over the network. So I will check initial value on the ledger. I will interact with the smart contract and then like send a new value, like store a new value there, and then check the values. So let's see if this works. Of course, I didn't expect to run the Groovy example here now. Yes, looks quite okay. Okay, so initially we have a 0 as a value, and then if we store a value, we have then the other value. So as you see if you retrieve. So is of course pretty simple code. And if we look into the blockchain, what happens, we see for each of those calls that change the state, a transaction has been executed. So when I just read state, I don't have to perform a transaction. But when I want to change state, I have to do a transaction. So I do this contract call, and then we see, okay, it is sending. So my address on the computer is sending something to this contract, which is like the object, the instantiated object living in the Ethereum blockchain. And it sends this transaction data. So byte encoded just the parameters it calls from the function. And that's it. So also this is then public for everyone to see. So it is public. The interaction with the smart contract is public, and the data you send is public. So it's very important to be aware of. All right. So there's some other cool stuff. So as I told before, I'm also a test containers maintainer, and there is a test containers integration for Web3j to allow you testing of your smart contracts using test containers and Docker-based Ethereum setup. That's cool. Yeah. And so since we are here at an Oracle event, maybe as a last disclaimer also, like if you're using Oracle Cloud and you want to do stuff with blockchain, what are the easiest things that can get going? Of course, you can always just get normal computing resources like virtual machines or whatever and set up whatever blockchains you want to have. Then most of them provide good Docker images to do this. But there's also something called Oracle Blockchain Platform, which is more of a ready-to-use service, and is a platform as a service kind of thing that provides you Hyperledger Fabric-based blockchains. So I didn't talk about Hyperledger Fabric here in detail. It's also an open source blockchain technology, and it's mostly suited for company to company blockchain systems. So not for public blockchains. With Hyperledger Fabric, you're not building a public blockchain. But if you are like a set of supply chain companies or whatever, and you want to have some interoperability with each other, where it's important that you don't have like everyone is kind of not 100% trusting each other, then you can delegate the trust into the blockchain technologies. Then it makes a lot of sense. And then what is super important that it has support for hybrid networks, because if you set up a blockchain network and you have all your nodes in the same cloud provider, is not a good idea, because then you lose all this nice resilience properties of a decentralized system. Because if this one cloud provider goes down, or you have censorship problems with this one cloud provider, then the whole network goes down. So super important to have nodes then outside of Oracle Cloud, and the same somewhere else. So if you're running on IBM or on Amazon, you need to have nodes running in other clouds to have a good heterogeneous blockchain network. And then the other thing that is quite cute and maybe a good solution, if like the manager comes and says, "Oh, we need blockchain in our product, we need blockchain in our services," you can just use the Oracle blockchain table feature in your Oracle database, and this changes a table to be append only and chained using cryptographic hashing. So this is not a really blockchain by most definitions of blockchains, which means they're also a network and so on. But it is enough when you just need an append only ledger that is has a high integrity and tamper-proofness secured by hashing. What is important here now, of course, is that you have to share those hashes with other parties in order to detect a potential tampering with the data, because in theory you might be able to recalculate just the hashes or something. So you have to publish those hashes somewhere that someone would see, oh, you manipulated something. Alrighty, so that's from my side. This is just like GitHub sponsor links from me personally, but more importantly for the test containers project. So if any of you are test containers fans using it a lot professionally and so on, we would be very happy if you, I don't know, like to sponsor $5 a month or whatever. Happy about everything. I would be, I hope I could, yes, inform you a bit about blockchain and the historic concept and the context of it. And I would like to engage in whatever kind of questions you have, try to answer them, have some kind of discussions, whatever. Yes, thank you.
Okay, that's great. Thanks, Kevin. So we've got the Q&A box or the chat box. If you've got any questions that you would like to ask, we've got a few minutes for questions. So we've got from Babu, a thank you for the presentation.
You're welcome.
You do need to give it a minute because people take time to type their questions in. So it can be a little. So if anyone would actually prefer to speak, I'm quite happy to. If they put their hands up, I'll allow them to talk on here if they prefer.
Yeah, that would be also cool.
And then there was silence. So obviously you've taught us everything we need to know about blockchain. Oh, question. How many external nodes is recommended from one's main cloud environment?
Yes, so Kevin, this is a very good question. It depends on the consensus algorithm that is used. So assuming this is a proof of authority based network you're operating, so proof of authority means you have an authorized known set of nodes that are allowed to validate, then a lot of them either mean majority or 1/3 for making blocks persistent. So now this would mean that you should not have the majority of nodes in a single data center, because then if this data center or this one cloud fails, the whole network fails. There are more complex attack and failure scenarios actually with regards to network partitioning that could happen. So you should not only think about the different providers, but also like global distribution in which areas, like in the US, in Europe, in Asia, because there could always be network partitioning happening between those areas, either by attackers or by just network failures. And then if you run into scenarios where like both both partitions have a seemingly majority or like enough to persist nodes in the network, then once the network partition is over, you will have basically a conflict and it will be hard to decide which one will be the winning chain. And then you would potentially lose transactions you already saw to be final, which is of course can be a problem, or it can mean people might be able to attack it using double spending attacks, meaning executing funds multiple times. Yeah.
Okay, that's cool. We got another question. What is the valuable use case for blockchain, please?
So we have this famous use case, which is cryptocurrency and crypto economics. This is well understood, and I think it is a valuable use case, although I'm not a big cryptocurrency guy. We have other ones that are more classic. We have a lot in the area of supply chain management, where it is about the public ledger part is the important thing. So having this public ledger that is append only, that is transparent for all parties, and that basically guarantees you an audit trial across a set of parties where parties potentially not trust each other 100%. So there it makes a lot of sense. It makes a lot of sense everywhere where you need to provide a public ledger for government purposes, for example, for citizens, like kind of public registries. So we have this in Germany. We have some use cases we try to implement with cities, like for example, if you're forbidden to park somewhere, it's like a stupid example, but still, if you're forbidden to park somewhere, there's a lot of paperwork involved in setting up the certificate. Like then the city will put a sign in there, and then someone can just move the sign and say no, it was standing there or whatever. All kind of manipulations can happen. But if those also by governments are published in public registries for everyone to see, you have more transparency and more trust, and you can potentially digitalize more systems. There are a lot of use cases that use a public ledger and a blockchain at a certain point to establish trust in identities. This is a whole different use case field. It's called self-sovereign identity. It's a bit more complex, but it is a use case we will see in the future. So as opposed to the centralized identities we have nowadays, which are controlled, for example, by Google or someone or our provider, the self-sovereign identity tries to bring the identities back to the users and sharing the data by the user, and it uses certain cryptographic elements on public blockchain ledgers for generating cryptographic proofs, for allowing data sharing without having the data centrally everywhere. Very cool topic, will come in the future, I think. And what I'm personally very involved in is using a blockchain in the context of science and research for potential use cases in the domain of open data and open science for countering the reproducibility crisis we have currently in science, which has to do with like lack of transparency in the research process, actually. So then just doing timestamping, for example, of the data in the blockchain.
Cool. We do have another question. Why do you think we should go for cryptocurrency?
I don't think we should go for this. No, I don't. I'm not commenting on this, but I think it is a valid proposition to think about this completely decentralized financial systems. It's cool. I don't know. I can imagine there is value in those systems, especially for nations that have less stable currency situations and systems. It is a complex topic and I'm not an expert about it, but I see in general that there can be a value for decentralized payment systems in a society or in different societies.
Cool. And I think on that note, we say thank you very much, Kevin. I think that was a great talk, a really great overview of the blockchain tech. And thank you very much.
Happy to be here. Thank you.